Hello and welcome, guys, to another session in the Mind Grid. Today, we are talking about Intro to Networking again, and this is the third part of our video series. Today, we're talking about the L3 extension header parsing in the IP layer. And again, this is a series using MyHDL, which is a convenient way to write RTL or FPGA code or ASIC code and test it without needing advanced tools like simulators and synthesis tools, etc. All right, so again, the summary is that we are looking at parsing today, and the extension header parser is going to be our main aim. The same things will follow. We'll go analyze state machines, timing diagrams, etc. All right, so just as a quick recap, we already looked at the L2 parser in the first episode, then we looked at the L3 parser. Today we are kind of finishing up the L3 parser, which is like the tail end. If you have extensions in L3 parsing, just because we have so much data in a single clock cycle, it is not straightforward to parse out multiple extension headers or multiple messages in a single clock cycle. That can get very complicated in timing closure. So from the perspective of writing good timing closure and code that can be synthesized, one has to write and think about code ahead. And so we have kind of split up the L3 parser from the extension parsers, and we can instantiate multiples of these extension parsers to build, let's say, a stack of extension headers. Now, the limitation in this approach is that we can only support a certain number of extensions. So if you want to do infinite number of extensions, then you have to obviously think about a different approach. But the approach here assumes that you can support 2 or 3 or 4 extension headers, and you can tag along these modules to extend. So again, the long-term objective is to get to the GRE parser and the GRE strip block, which can remove the GRE headers and get you the inside packet of the tunnel. All right, the timing diagram kind of remains the same. A quick shout out to Wavedrom that helps us design these waveforms very easily. I have done another video tutorial on Wavedrom. So if you haven't seen it, I would say go find it. I'll leave a link in the description so you can go follow Wavedrom, and it makes it fairly easy. Now, here I've already described this in previous episodes that the clock and data, there's 256 bits of data here because I'm trying to achieve, let's say, 100 gigabits running at maybe about 400 megahertz. So I need 256 bits of data, and the data is organized in a certain way. So I have 16 bits of header, and then data starts after the first 16 bits of header. In that header, I can carry a lot of metadata for every packet. Now, this one single unit of data between the start of frame and end of frame, or start of packet and end of packet, is what is called as a packet in Ethernet. If you're not familiar, I would say go look up Ethernet and get some little bit awareness about how Ethernet works. But within this packet, you can now see that we have parsed the L3 SOF and L3 tag, which tells us exactly where which byte is where the L3 header will start. The L4 SOF and L4 tag is kind of our objective because that's what we want to strip. The GRE lies at layer 4. But what we are talking today is somewhere between this L3 and L4, and it will be called L3 extension SOF and L3 extension tag, right? So we are going to find that. Now, again, in a graph form or a graphical form, you can see that this is a packet. This is an Ethernet packet, and it'll always start with layer 2, then be layer 3, and there'll be layer 3 extensions, and then there'll be layer 4 GRE, and then there'll be the data, right, which will be the payload, right? And because this is inside GRE, we will assume something, because GRE can carry an L2 inside it or an L3. In this case, we are assuming it's an IP layer, and so we will basically extract the IP and payload and attach it to the layer 2 outside, and we'll basically delete everything here. Layer 3 will get deleted, and this GRE will get deleted. By the end of the episodes, we expect to achieve where all this layer 3 and GRE is removed, and this inner stuff is attached to the layer 2, and that'll be the next packet. So this is also known as detunneling or decapsulation of the GRE, right? That's what we are showing. Now, on the top, I'm showing you how many kinds of, as you do the parsing, as you peel through the layers, you have to create new markers. So when we did layer 2, we already started with L2 SOF and L2 EOF and tag. right? And that's what we started with. As we went through the layer 2 parser, we got L3 SOF and tag. When we went through layer 3 parsing, we got L3 extension SOF tag or L4 SOF and tag. So those were created. Now when we'll finish the GRE parsing, we'll get the L5 SOF and tag. And using all these markers, then we'll be able to strip or remove the GRE headers and whatever is required to make a ideal packet, right? Okay, next let's look at extension headers in IPv6. Now this video is not concerned with IPv4 extensions because they are usually simpler. So I'm going to cover the IPv6 extensions, and there are many kinds of IPv6 extensions like hop by hop, routing, fragment, and these are in addition to the regular header. So the regular header, I think I showed in the previous episode, is 40 bytes for IPv6. And then beyond those 40 bytes, you will have all these multiple headers. And it's like a linked list. You're going to chain these headers one after another, and you're going to basically keep parsing through these headers till you reach the end, at which point you might see layer 4, which would be either TCP or UDP in most cases. Our objective is to find that. So we don't really have to understand each header type, but we have to be able to generally take, for example, this hop by hop header and other headers. They all have a similar structure. So they have a next header. Next header might show either a following extension header or TCP UDP. There's the extension header length, and this length is in multiples of 8 bytes. And then there are options and padding and options and padding and all the data that follows here, right? So once you have these fields parsed out, you can basically apply the structure over and over again, and you can keep parsing and keep peeling through the layers of extension headers. Now, in reality, doing it this way, you will be limited to a certain number of extension headers. In our case, if I were to design this in an ASIC or an FPGA, I would probably limit myself to, let's say, 2 or 3 or 4 maybe extension headers, and that way I can keep a high, good timing, as in get good synthesis timing, and at the same time keep my design relatively small, right? Because when you run these designs at 400, 500 megahertz or even beyond, you have to be very careful about how you're constructing your logic. So this is a good approach in getting a high efficiency and high bandwidth out of your code. All right, so let's now look at the code. Now this time I'm going to show you the code instead of showing it through the simulator, because I've already shown you layer 3. I'm going to just show it in slides. So layer 3 extension is going to look similar. I have reset and clock, and then I have L3 from the layer 3 or from a previous layer 3 if you're getting it from an extension header itself, because you can chain multiple extension headers. This is the input layer. So input layer has L3 extracted, which is all kinds of headers that have already been extracted. Now L3 is L2 interface, L3 interface, L3 extension interface, and L4 interface. So in most cases, if it's coming to extension header parsing, then this L4 SOF hasn't happened yet. That's why it's coming into extension header. But in case if it has already happened, then L3 extension should not be doing anything. It just needs to bypass, right? So we would probably have to take care of that. Now the output of this is L3 P extract, which is now the output, which is the extensions. So L3P, L2 interface, L3 interface, extension, and L4. It's very similar, except that this is the output of the extension headers. And the input has an extension as well, because you can chain these. So you can put multiple extension headers one after another, and that's why you have the extension. Now, most of these, like I mentioned in the previous video, leave me comments if you have confusion about this. But what happens is that you indicate L2, right, or L3 extension start, L4 extension start. That's what, and the L2 itself, like I showed you in the previous picture, if you remember this picture. So each of these tags will give you a start of frame and tag. When you give L3 extension, you'll get L3 extension SOF and tag. And when this goes into this next level parsing, you'll get all of these, and then you'll produce this. And then we get all of this, and then you'll produce this. And then you get all of these, and then produce that. So now if you look at this interface, you can see that that's what we are getting input. and then these are the outputs, right? These are all the inputs. The first two rows are the inputs, and then this last row is the output. Now let's take a quick look at the state machine. The state machine looks like this. You have just two states, idle and data. And once you get the start of frame for the L3, you basically start parsing. And L3 start of frame, once it has been achieved, actually this is not L3 start of frame, this is actually the extension start of frame, because this parser, remember, is the extension header parser. So it's already, L3 is flagging you that it has received a start of frame for either the extension headers or the L4. So those are what is coming in, and you have to check that. And if this is the start of frame and the L3 header, so if you have if you have the header, which is probably going to be contained within this clock cycle or not, that's the decision you have to make. Because if it's contained within this clock cycle, you'll wrap up right here and you'll go back to idle, right? You're done. You don't have to keep counting till the header is exhausted. And so that's why you have the data state, is that once you know the length of the header, in the data state, if the header lasts multiple clocks, you're just going to keep counting the clocks, and eventually when you get the end of the packet, you can go to idle. So that's the general state machine. Now on the left side, you can see how it's written, how the code looks like in MyHDL. So if the state is idle, then you basically start parsing. If you get the SOF, if the SOF is received, then you basically extract all the header fields. The next header, the protocol, the version, those are already being provided to us. And then we extract from the data, we extract this next header, length. Those are the two critical things. Once we have extracted those two, then I think everything else falls in place, because now we have to just make a counter. This tag next is actually a counter based on this length. Once we have this counter, we just keep counting like the state machine shows. We either finish up in the idle state or keep going data and keep looping in the data till all the header is exhausted. And then once the header is exhausted, either we will produce a L3 extension SOF or L4 SOF. And that what will that depend on, right? That'll depend on the fact that when this header is indicating the next header, like we had said before, the way the protocol works is that there is this next header field inside the extension headers. So based on this next value, the next header, if it's a TCP or UDP, then you will say that whatever's following protocol is going to be a layer 4 protocol, or GRE also. Actually, they should say 6 or 17, or a GRE. So I think I'm missing one. So I should have a GRE here, and once I get the GRE, I'm going to indicate the L4 SOF, right? So that's what I'll do here. And then the same thing here. You can see that if the in the data state, basically you're just counting by subtracting 32, because whatever the word count is, every clock cycle you'll chew 32 bytes, and so it's subtracting 32. And then as soon as I get next header equals 6 or 17, when I get to the end, which is tag next, so if the end of this extension header lies in the clock cycle, then you basically signal either the SOF for the layer 4 or the SOF for layer 3 extension. Another layer 3 extension, which is a chaining of extension, is seen. So that's what's going to be passed on. So that's it for this video, guys. As you've seen here, that parsing the L3 extensions really is it could be complicated, because within a single clock cycle you could have multiples of these headers. Now, because if each header is like 8 bytes only, or let's say it's a little bit more, let's say it's 12 bytes. So you could have, 4, let's say not 4, but let's say 3 plus headers. So 3 plus headers would be hard to parse within a single clock cycle. It could be hard. I mean, I'm not saying that it's impossible, but it's hard to meet timing by designing that in an FPGA or an ASIC. So that's why we have designed a parser that just parses one extension header, and then we can daisy chain these extension parsers to produce n number of these extension headers parsing. And then we showed exactly how the IOs look like, and then we show you how the state machine looks like. And using the state machine, you can parse the IPv6 extension headers. So with that, I guess we have come to the end of the video. If you had any comments, if you have confusion about certain things, certain aspects of MyHDL, let me know. I can make another video to discuss any of the issues, or I can answer your questions. But if you liked it, give me a thumbs up, and don't forget to subscribe to my channel. I'll catch you in the next episode of this series. Until then, take care and bye-bye.